Okay, let's read another net change example given the graph. This is example 2. It says the velocity of a remote controlled car traveling in a straight line is given by the graph below. So we have a remote controlled car and it's traveling in a straight line. This is its velocity. So basically the car is just going back and forth like this. In fact, I'll draw a picture of it in just a second. But this is the graph of its velocity in feet per second. So at the onset, the remote control car is going 0 feet per second, but then its velocity is negative, so immediately the car starts to back up. And in fact, it backs up. And then at time t equals 2, it actually starts to go forward, and that's why its velocity is 0, because it changes direction and starts to go forward, and it has a positive velocity. So we want to figure out, if we read the question, describe the car's motion during the first second. Well, I actually just explained that, but because its velocity is negative, it's going backwards. So this question has several parts. Anytime, a velocity graph is below the t-axis or the time axis, that means its velocity is negative, which means it's traveling backwards. So if you want to draw a picture of that, it would just basically, here's the remote control car. It's just going like this. And in fact, it's going backward from 0 to 2 even. Next question. What happens at the moment t equals 1? The acceleration is 0. Now this is a little bit more advanced, but not really, because if you look at this graph and you draw the tangent line at t equals 1, it's 0. Now the slope of the tangent line for velocity is acceleration, so it makes sense that the acceleration would be equal to 0. What that means is that the car is neither speeding up or slowing down. Okay. What is significant about the time t equals 2? Okay, so let's keep reading. It says the car changes direction and it starts going forward. Now let's go ahead and see why that is. That's just because the velocity becomes positive. So we go back and look at the graph. At time t equals 2, the velocity becomes positive again, which means that the car starts to go forward. So if we were to keep drawing what happened to the car, after it started going backwards from t equals 0 to t equals 2, it would start to go forward again. Alright, so if I wanted to try to do like a real life example of this car, here's the car right here. Okay, it's backing up from 0 to 2, okay, and then it goes forward. That's all it really does. Okay, as complicated as this graph might look, that's all the car does. It backs up, backs up, backs up, and that t equals 2, it goes forward. Now it will accelerate because the slope of the tangent line increases for a velocity graph. So you can imagine it goes like this, and then whoo. Okay. How far is the car from its starting position at time t equals 4? So this is the gist of what we're getting at. Okay, we answered some preliminary questions, but how far is the car from its starting position? That is displacement. And again, if you take the integral of velocity, you get displacement. So in order to figure that out, we want to find the area under the curve from 0 to 4. And we're going to use the trapezoid rule just because it's a curve and trapezoids tend to fit the curve better. So step 1 for finding net change of a graph is to determine the signed area under the curve using geometry or approximating it using Riemann sums. We can't use geometry like the last example because it is a curve, so we will have to resort to Riemann sums. Remember, for net change, I've said this every time I've done a net change problem. For net change, you want to find the signed area. Anything that's below the x-axis needs to be negative. Okay, so here's our graph. We're basically going to be drawing 4 quote-unquote trapezoids. Now, it is the trapezoid rule, but the first 3 are actually just triangles because of the way that the curve is drawn out. It ends up just being 3 triangles and a trapezoid. So here's our first 2, Our third one's going to look like this. Okay, that's because basically the height, the initial height of each of these is 0, but then when we get to the fourth one, or you could say the first base rather, when you get to the fourth base, it actually does have a height, as does the second base, and so the fourth one ends up being a trapezoid. So if we approximate the area here with these 4 trapezoids, we should get a pretty good idea of the signed area of velocity, which will give us the displacement of the remote control. Remember, we have to subtract this, which makes sense because initially the remote control car backed up. So basically it backs up, and that's going to negate some of its displacement. So if the car ends up right here, it only started here and went to there. We're basically, when we make this negative over here, we're basically subtracting that amount that it backed up. Okay. So let's find the area of these 4 shapes. It is kind of geometry because, like I said, these are just triangles. This first triangle is just half of one block, so it's 0.5. Same for the second one, half of a block is 0.5. The third one is going to be basically half of these 3 blocks, which is just 1.5. And then finally, we have the area of the trapezoid, which again is 1/2 times the height times b1 plus b2. Well, b1 is 3 and b2 is 8. And the base is just 1, so it's 1/2 times 1, 3 plus 8, which is 5.5. And if we add up all of these, that will give us the signed area under the curve, which ends up being, that last one got kind of cut off, that is 5.5, if I can put it on there. There we go. If we add up all of these numbers, making sure that these first 2 triangles are negative, because it's signed area, so it's -1 in effect. If we add these up, we get -1 plus 1.5, which is 0.5 plus 5.5, which is 6. So this is just our answer. So let's answer verbally. The car traveled 6 feet from its starting position. Okay. I could probably word that a little bit better. It's changed in position at 6 feet. We know that a total distance traveled, basically we would just consider these positive. So we would have 2.5 plus 5.5. So total distance traveled would be 8, right? But basically what happened is that it backed up a foot. And so it had to travel back that foot just to get back to its starting position. So there's a 2 feet difference between its total distance traveled and its displacement, which again was just 6 feet. So you go back to basically the track of the car and what we're trying to answer. Here's where the car started. It backed up. Its total displacement from where it started is 6 feet. And that's ultimately what we've answered by finding the signed area of the velocity graph, which it gave us. That's it for this question. If you have any other questions about it, let me know.